Hi, my name is Andy Kaylor. I'm a compiler engineer at Intel, and I'd like to talk to you today about the FP model command line option for floating point control. As you may know, there are a lot of settings that the compiler uses to control its behavior with regard to floating point optimizations. The most familiar ones are probably fastmath and FP contract. But there are a lot of more fine-grained options that you can control things like whether the compiler allows changes to the rounding mode, how it handles denormal values, whether speculation is allowed or not. And each of these is controlled by a different command line option, and in some cases, more than one command line option. So we'd like to have a way to simplify that. The solution to that I'd like to talk about today is the FP model command line option. A similar option has been supported for a number of years by the Microsoft Visual C++ compiler and several Intel compilers, but it was only very recently introduced within the past year, I think, to Clang. And so the idea behind this option is that you select from one of a small number of models that control the overall behavior and present a default value for each of the settings depending on the model that you've chosen, and the hope is that these small number of models will cover the vast majority of common use cases. If you do have individual needs beyond these, individual settings can be overridden as needed. The other thing that I'd like to emphasize here is that this doesn't change the way that the floating point controls are represented in LLVM IR. This is just an option that the front end uses to let the user specify which group of settings they want to use for generating the IR. So now I'll go through each of these models individually and describe how they're used and what settings they have. The first model is the precise model. This is typically the default for compilers and is used when you want reliable and accurate results. The primary feature of this model is that most value changing optimizations are disabled, so all of the fastmath flags are cleared. The one thing that's somewhat value changing in some circumstances is that floating point contraction is enabled in circumstances where it's allowed by the source language standard and supported by the target architecture. So for instance, the C language standard allows floating point operations to be contracted if they occur within the same expression in the source code. So the precise model also allows that. In the precise model, we are preserving denormal values. So this is somewhat slower on some architectures, but it allows a broader range of values to be represented and used in your computations. No floating point environment access is allowed in the precise model. So what this means is that the compiler is free to assume that the default rounding mode is always in use and make optimizations based on the default rounding mode. It also means that the user's program can't check floating point status bits or unmask floating point exceptions because the strict exception semantics are not preserved. This model generally is intended to conform to the IEEE 754 floating point implementation standard, and so users who want that sort of conformance will choose this model. The next model I want to talk about is the FP model equals fast. This is the model that you would choose if you want the best optimization and are willing to sacrifice a little bit of predictability and repeatability in the results of the numeric computations. So this mode enables all fast math optimizations. Therefore, it's not a value-safe mode. If you compare the numeric results that you get with this model to the numeric results you would get with an unoptimized program, they won't necessarily be the same. The fast model also enables floating point contraction formation of FMA instructions anywhere that the backend thinks it's profitable, not just within a single expression. So if the optimizer is able to bring together, for instance, multiplication and addition, and it thinks that it would give better performance to combine those into an FMA instruction, it will be allowed to do that in this mode. And also, denormals are flush to zero in this model. This gives significantly better performance on some target architectures. It also will allow some algorithms to converge faster. So it's a nice performance gain at the sacrifice of a little bit of range and representation of values. Like the precise model, floating point environment access is not allowed with the FP model fast, so the compiler will assume the default rounding mode and it will not preserve the exception semantics. The final FP model is FP model strict. This model is meant to preserve all source semantics for floating point operations as exactly as it's able. So all value changing optimizations are disabled. No fast math in this model. Floating point contraction is also disabled in all cases with the strict model. Denormal values are preserved, so you can use the full range. And finally, the most important characteristic of the strict mode is that it allows full access to the floating point environment. So for instance, the user's program can change the rounding mode at runtime, and no optimizations will have been performed that make assumptions about what the rounding mode was or would be when the program is executed. And also full exception semantics are preserved, so you can check the floating point status bits or unmask exceptions and not have to worry about spurious behavior introduced by, for instance, the compiler speculatively executing a floating point operation that might not have been executed according to the semantics of the program. The trade-off with this mode, of course, is that many optimizations are inhibited, and so you don't get quite the performance if you use the strict floating point. Finally, I have my call to action for this. As I said, Clang currently supports the FP model option, but consistency across languages would be great for people who use more than one compiler and more than one programming language. So if you are involved with another front end, I would encourage you to implement this and provide support for this. The other call to action here is provide some feedback. So if you think that we need additional models that beyond the 3 that I've talked about today, or if there's something about the settings that you think should be changed, please bring this up. You can start a conversation on the LLVM Dev mailing list, or feel free to contact me directly. My email address is andrew.kaylor@intel.com. Thank you for your time.